Alright, today we're going to talk about periodic trends and a little bit about how the periodic table is organized. And so to start this out with your students, a good thing to do is have them take some shapes, or there's all kinds of activities out there where you can do this, where they have to kind of figure out how to order these things together. One of the activities I have, it's like circles with little things that jut out. I've seen before periodic table aliens, periodic table people, all kinds of things on the internet that you can pull off. And basically they just have a series of pictures and they have to put them in some sort of order, and you kind of go from that model to the periodic table and how it's arranged. And so it's a good kind of activating strategy to get them thinking about organization and patterns. And this is a really, really good opportunity to have your students kind of examine some data and figure out what the periodic trends are themselves without you just telling them what they are. And so this is one example of some data that you could give them, and basically it shows the atoms as they're lined up on the periodic table. Right here is where the transition metals fit in. They've just taken those out of this model to make it a little easier to understand. And so you can ask your students some questions here. You know, what are the trends? What do you see? What's going on with atomic radius or size as we go up and down the columns and as we go across the rows? And so hopefully your students can see them, that size increases as we go down the column. It gets bigger and bigger. And size also increases as we go left across the periodic table. And so students can look at this and come up with a pattern. You can ask them some good questions about the trends. Are they always constant? Like, does it always follow the trend? So here in this column we see, yes, it does. Size increases all the way down. But for the row, we see it's not always the case. And so neon 0.7 angstroms, and then fluorine 0.64, and then oxygen 0.66. And so we have a little bit of a discrepancy there in our trend, and that's why we call it a trend, because it's not a constant thing. It doesn't apply all the time. But we can say in general, increase down the chart, increase left across the chart. And now we want to talk about and we want to understand why that is. And so here are the reasons. So remember we talked the other day about, well, in the last lesson, about the Bohr model, and we talked about the quantum model. And so the reason size increases as you go down the column is because you're actually adding shells, or there's energy levels. So just think back, remember we had hydrogen. Hydrogen was in the very first row on the periodic table. And so if you were to draw your Bohr model for hydrogen, you'd have your nucleus, and you'd have one energy level or shell with your one electron there. And then let's say we went down to lithium, which is the next atom down. Since lithium's in the second row, your picture will look very different, because instead of just having one energy level or orbit, you would actually need to show two. And so just relating back to the Bohr model, you can see then there's a big difference here in size. And so that's pretty easy to understand, and most students understand that size increases as we go down the column or down the group because we're adding shells. Now this explanation is a little harder for students to grasp. And so as we go left across the row, all those electrons, those outer electrons, are in the same shell. Because we have less protons as we go left, we have less attraction for those valence electrons. And so you can imagine with less attraction, your atom is able to spread out a little more. And if we go back to the original slide, you can see that that size difference is not that great of a difference here. Okay? And so nitrogen and oxygen both have their valence electrons in the same shell. It's that second energy level, okay? But nitrogen has less protons in the nucleus. And you have to think about, well, what's attracting the electrons in there in the first place? And it's the protons. And so because there's less attraction here, because there's less protons, this is able to spread out and get a little bit larger, whereas the oxygen, which has more protons, is able to pull those electrons in a little bit, and it's a little bit smaller. And so it's all about shells when we talk about the columns, and you're going to see that repeated over and over as we look at the other two trends. And it's all about protons, number of protons here. And what we actually call that in chemistry is called effective nuclear charge. And so the effective nuclear charge for nitrogen is less than the effective nuclear charge for oxygen. Since there's less effective nuclear charge here, it can spread out, get a little bit bigger. More here, kind of smooshes in a little bit smaller. All right, so here's another representation of the data that you can kind of show your students and ask them to figure some stuff out. Or give them the data. That's what I do for my high school students. I actually give them the data and have them make a graph themselves, either on Excel or some other, or on paper if you like. And so what I have here is lithium through neon. That's the second row on the periodic table. And then we also have sodium through argon. That's the third row on the periodic table. And so you can see as you go across the row, ionization energy, which is what this graph is going to increase as you go right across the row. And it works both rows, second row, third row, okay? And then we can also use this graph to look at our columns. It's a little bit harder to see though. So lithium is here, sodium is here, okay? Those two are in the same column or group. Sodium is a little bit lower, or is below lithium. And so lithium's ionization energy is a little bit higher. So ionization energy then is going to increase, and we'll show this in a minute, as you go up a row, up a column, and to the right on the rows. So it increases as you go up and right. Size increased as you went down and left. Okay? And so we need to step back a minute. Size was pretty easy, explanatory what it means, you know, how big or how small the atom is. Ionization energy is the energy required to remove an electron, actually from a gaseous atom. So the energy required to remove an electron. And so if you look lithium to neon, neon has a high ionization energy. That means it's hard to remove an electron from neon. Lithium has a very low ionization energy. That means it's easy to remove an electron from lithium. Okay? So thinking about that, we can start to explain a little bit why the trend is the way it is. And another thing you can look at with this data is that the trend's definitely not consistent. You see dips here, and it repeats here as well. The reason for the discrepancy here, for beryllium, its electron configuration is 1s2, 2s2. The electron configuration for boron would be 1s2, 2s2, 2p1. And if you look at the data, you can see that the electron being removed from boron is a little bit easier than the electron from beryllium. And it's because of the energy level that the electron is in. And so boron's valence or last added electron is in a p subshell. Beryllium's in a s. This is a higher energy electron, so it's easier to be removed. And so this higher energy electron in the p is slightly easier to remove than this s electron. That's pretty hard for your students to understand. Let's look at this example. It's a little bit easier. So nitrogen be 1s2, 2s2, 2p3. And then for oxygen it'd be 1s2, 2s2, 2p4. And so if we think about our orbital diagrams that we drew the other lesson, I'm just going to look at our 2p electrons because those are the focus. And if we draw out our orbital diagrams, you can see here 2p3s. We have 3 electrons in the p subshell. And we're going to follow Hund's rule, and we're not going to pair those up. We're going to fill them in, right? Hund's rule says 1 in each orbital before pairing. So there we go. For oxygen, we're going to do the same thing, except now we have 4 in the p. So 1, 2, 3, and then add another 4, like that. And so when you think about removing an electron, for nitrogen, we're removing this one, the last added. It'll be the first one removed. For oxygen, we're thinking about removing this one. So thinking about electrons and the fact that they're negatively charged, why do you think it would be a little bit easier to remove this one in oxygen? What's this electron right here doing with this other electron in the same orbital? And so what's going on right now is this electron is experiencing repulsions with this electron. And so it's slightly easier to remove. Whereas up here, we don't have any repulsions because none of the electrons are paired within the orbitals. And so it's a little bit harder to remove. A little more stable here because we have no repulsions. Okay? So, and that follows along and along. And as you increase and go down the rows, this discrepancy gets less and less and less visible. So I just want to point that out. That goes a little bit beyond. But still, trend not always followed perfectly. All right, so now for the explanation. So again, here we have our definition, energy to remove electron. How does the trend go? It increases up and to the right. Well, why is that? Remember I told you when we're talking about these rows, our focus is on the number of protons. When we're talking about the column, our focus is the shells. So as you go to the right, your number of protons is going to increase. And so if your protons increase, what happens to the attraction? It's going to increase too. And if the attraction increases, it's harder to remove the electron, so more energy is required, and so your ionization energy increases. On the column side of it, as you go up the chart, your number of shells decreases. And when the shells decrease, this actually has two effects, and we'll talk about those. When you have less shells, number one, the electrons are closer to the protons. That usually makes sense for most students. And when the electrons are closer to the protons, they feel more attraction, so they're harder to remove. But there's another effect going on as well. When you decrease the number of shells, you actually have less what's called electron shielding. And so you can imagine, here's my protons. So if I have an atom with 3 shells, so an atom in the third row, this valence electron right here on the outside is shielded from the proton's attraction by these other 2 shells. And so whenever you decrease the amount of shells, say maybe to 1, this electron in the valence shell isn't shielded by any other electrons. And so it's more attraction here, less attraction here. Less attraction, easy to remove, low ionization energy. More attraction, hard to remove, high ionization energy. Okay, so that's your reasoning for there. Now, a good thing to make a connection with here is back with our ions and naming. So if you remember, thinking about your periodic table from left to right, the stuff on the left, those were metals, right? And the stuff on the right of your periodic table, those are nonmetals. So think back to your charges. The stuff on the left, what kind of charge did those ions have? They have positive charge. Stuff on this side, what kind of charge do they have? Negative, right? And so this helps to sort of explain that. Metals on the left-hand side of the chart have really low ionization energy, so it's easy to remove an electron. And that's what happens to them. They lose electrons and get positive charges when they form ionic substances. Nonmetals, on the other hand, have really high ionization energies. They don't want to lose electrons, and so they don't. They actually gain electrons and become negatively charged. So that kind of helps kind of pull the pieces together. Okay? Here's another example of data. So we've seen some little circles data. We've seen an actual graph. And here's another figure. It shows your periodic table. This one actually includes the transition metals, which I like because with the transition metals, you see lots of discrepancies here. Not a lot of trend going on with the transition metals, which is usually why we leave them out. D electrons there make their chemistry very different. But let's focus on our first 2 columns and our nonmetals over here. You can see for electronegativity, which is what this is showing us. Electronegativity is going to increase as we go across our chart. 1, 1.5, 2, all the way up to 4. And it's going to decrease as we go down our chart, as you can see with the figure. You may not be able to see this, but there's a column missing here. We stop here at fluorine, chlorine, bromine, and iodine, and so the noble gases are missing from this figure, and we'll talk about that in just a minute. So what is electronegativity? Electronegativity is an ability to attract electrons, and so it increases as you go up and to the right. The reasoning is very much the same as ionization energy, except the definition is different. So why does it increase as we go right? Same shell, right? All the valence electrons are in the same shell. Protons increase, effective nuclear charge increases, so therefore the attraction increases. And that's what electronegativity means, higher attraction for the electron. Going up, just like with ionization energy, we have less shells, so the protons are closer and there's less electron shielding, and so the attraction is going to increase there. So this pulls us back to why are noble gases not included in the chart. And so let's look at a noble gas. Let's pull in what we learned a little bit about the other day. So neon, electron configuration, 1s2, 2s2, and 2p6. And so if we draw out our orbital diagram for neon, we'd have our 1s, our 2s, a little bit higher energy, remember, and our 2p, a little bit higher energy. And if we begin to fill in our electrons, 1s2, so I have 2 electrons here. That's a full orbital because there's 2 electrons present. 2s2, again, full orbital. 2p6, 1, 2, 3, and then I compare 4, 5, 6. And so if you look at neon, what do you notice about neon? Every single orbital, which is represented by these little boxes, is full. And so if all the orbitals are full, would neon need to attract electrons? And the answer is no. And so noble gases, there's no data for them as far as electronegativity goes. And so that's why they're left off the chart. Now, why do we care about electronegativity? So we care about ionization energy because it helps us understand why metals are positive ions and why nonmetals form negative ions. Why do we care about electronegativity? Well, electronegativity influences bond polarity, and then polarity, bond polarity, and molecular shape or geometry influences lots of other properties. It influences boiling points, freezing points, solubility, all kinds of different things that it influences there. So we need to kind of understand this concept. So when you have a covalent bond that has 2 atoms in it that have big differences in electronegativity, you have differences in attraction for the electron cloud, and when that happens you get a polar bond. And that's what this figure is trying to show based on the color differences. And so I'm going to make it a little bit bigger. What we're looking at here is HF, HCl, HBr, HI. And if we think about on the periodic table, hydrogen is way over here, and then fluorine, chlorine, bromine, and iodine, we're all in the same group, okay? So let's think back to our electronegativity trend. Electronegativity increases as we go up and to the right. And so if you look at these atoms, as I go up the chart, my electronegativity or my attraction for the electron is increasing. And so for this series of elements, fluorine would have the greatest electronegativity. And since we're looking at those atoms paired up with the same element, okay, fluorine, greatest electronegativity, therefore there's going to be the biggest difference in electronegativity here. And so what happens is the electron density is actually going to be pulled towards the fluorine. Because most of the electron cloud is over here, what you get is a partially, and that's what partially means, negative charge. Okay? And since the electrons are not as much over here, you get a partially positive charge. And you can show that with these symbols, or you can show it with an arrow like this. And you put a little line here to kind of indicate positive, and then the arrow shows you the direction of the electron pull. Because this happens, you actually get a polar bond, and in this case, a polar molecule, because you have two different sides, a positive and a negative. As our electronegativity decreases, we get less and less of a difference, and so less and less of a polar bond. And this figure is trying to show you that based on your color differences. So here we can see a lot of different colors, here a little bit, and here not so much. And so the electronegativity difference is not great here, so this is not going to be as polar of a bond as this one, the HF. So that's why we need to know about polarity.